Okay, and yeah, everyone's picture is frozen, so like Stephanie and CJ haven't moved, and yeah, something's weird. I don't know what. Actually, here, let me try this. I'm gonna, we'll just hope it gets better. I'll record it. That way, we'll at least have it that way. I'm sorry, it's not working well. Okay, question 16. We'll just set this one up. We won't go through all of it. It was on the homework that was due last night here. You're not given a whole lot of information, just given a graph. They're asked to find the centroid of the solid region. In order to be able to find the centroid, you need to be able to find x bar, y bar, and z bar, all three of those. And to find all of those, you need to find the moments. So moment about the YZ axis, or YZ plane. Let me write them in the same order they have above.
You want to go on the
X, Z, X, Y. So you need all of those guys, and we also need to go back and find the total mass. So we'll get one of them set up, so hopefully the rest of them kind of fall into place there. Let's take a look at the total mass, since that applies to every situation. I don't know why it's unstable. I'm not on wireless. Okay, so consider what this shape looks like from the top down. So if we think about the whole region that we are working with here, we are just in the XY plane. We know that this goes up to 20 because 20 centimeters. We know on the Y direction it goes up to 12 because 12 centimeters. And we don't really care about the fact that that 5 goes up to 5 there because we're not talking about the Z direction. Could you go back and find the equation for this line?
No.
Sure. Okay. Would you want to? Maybe not. But you guys know how to go back and find the equation for this line. So if you go back and find the equation for that line, that's going to be part of what you need in order to set some integration here. The other thing you're going to need to do is find the equation for this plane. So the surface that we're talking about is this plane over here, this triangle, and you have to go back and find equations for that too. Okay, because without that, you can't really finish this problem here. So there's two things that you need to do in order to be able to go through and set this up there. Okay. However, once you've got those, you still have to go back and set up your limits of integration. So mass for the whole system, in 3 dimensions. We're always going to have some constant. Yeah, assume uniform density. Okay, so if we're assuming a uniform density here, that means rho is just some number. So instead of K, you can just put rho in there if you want to. I don't remember how the book did it, how it notated it, but uniform density means there's no formula for this. We're not talking about getting worse, heavier, getting more dense if this relate is. All right, let's stick with dz, dy, dx. Your limits of integration for z are going to go from 0 to whatever the equation of the plane is that you come up with. Okay, and I didn't go through all those steps there, but if you go back to find the equation of that plane, there's a couple ways you can do it. I'll cover that in just a minute. Your equations for y, well, now if we go back to this picture down here, y is going to range from 0 to whatever the line is that you came up with over here. And then for x, we're going to go from 0 to 20, since those are your ranges for x.
That is too much work for a 1.
That is a lot of work for a 1 point problem. Yeah. That's very true. Let's do this. And that isn't even solving it. That's just getting the work. Okay, so here is the work for the rest of the pieces there, and we'll just look at the book to hopefully save a little bit of time. F of x, y over, or 5 over 12 equals y. That is the function of the surface here. So the way that comes from is, since this is just kind of slanted in one direction, it's like a cylindrical surface, which sounds really weird because it's a plane, but we're taking this line here from the origin out to this point over here where the 5 and the 12 meet, and we're basically just extending that in that one direction there. So there's no x component to this. That x component is just going to be parallel to it all the time there, and so they come up with that there. The way you could get that is a couple different ways. You can go through the long process of finding the equation for a plane. Now, it'd be okay. This one's kind of going to be a bit more difficult just because, well, that step's going to be a bit more difficult to go through and find vectors, find cross product of vectors, and all that stuff there. If you recognize that that x component is just not really contributing to this, you can really just find the equation on the yz plane of this line, and that would work too. But you have to recognize that that's how this plane is set up in order for that to work there. If you didn't recognize that, again, you have to go through and find vectors, find cross products, find normal vectors, and go through that whole process of finding the plane. But eventually, the equation for the plane you come up with is 5 over 12 y for this one. And so that's why that shows up in the top limit over here. The equation for the line we talked about is negative prefix x plus 12. Again, that's this line over here that they're talking about. And then the rest of it is, like we said, 0 to 20. Okay, so there's a total mass. The difference between each of the moments is you just add a new factor in there. So if you're talking about the distance from the xy plane, you're going to have to multiply by z. If you're talking about from the yz plane, multiply by x, and so on, and then a whole bunch of ratios. It is a lot of work for a one-point problem. That is for sure. Okay. But hopefully the setup makes a little bit of sense. I would venture that if you understand the setup, the most difficult part is probably just finding the equation of the plane, because that's not obvious how to go through and do that. But if you do have questions on it, feel free to send me an email, or if you did something, let's make an email. I never was everybody's email. Send me an email, I'll take a look at it. Okay. I haven't looked to see if anyone started the homework that's due this Sunday, and due to time, let's not worry about that. I'll come back and deal with that again on Wednesday. Let's get back to the notes here and see if we can finish up this section. So 14.7, we're on page 31. And so far, we'd set up this problem, and I'd said I got stumped, but I know the answer now. I'm unstumped on this one. And the thanks go to Miss Mary Hugh, to Bonnie. Bonnie is the one who actually figured this out, so you guys can go tell her that your teacher was very appreciative of it. So with this problem here, we're trying to find volume, and the point of this section is we're going to go through and convert it to different coordinate system. So for this one here, we have this sphere that we can kind of see in that sketch there. A sphere with a radius of 2. And then we have this cylinder that was cut out the side of this here. And so along that z-axis, that cylinder was parallel, and it went to the very edge of the sphere there. What we want to know, what was the volume of that piece of that cylinder cut out. So we still have some equal sides. We have that curved top and bottom coming from the sphere. So the setup we did for this initially isn't too difficult. We said that we're going to stick with dz dr theta as kind of our default. Since we're finding volume, we have an integrand of 1. But since we converted the polar coordinates, we have to make sure you go back and multiply by r. And the limits of integration hopefully come from where they come from. Our innermost limits were z, so they come from the sphere. We took the equation of a sphere and went through and solved it for z, and then wrote that in polar coordinates. So positive square roots on the top and negative square roots on the bottom. For the radius, we said the radius for this, we went back and looked at this region. And so from the top-down view of our sphere here, this is kind of what we get. So we've got that whole entire cylinder on the outside, but then that circle or that cylinder that we're kind of cutting through here. And that's what controlled our radius. And we haven't worked with a lot of problems like this, but what it came out to be is that our top limit of integration was going to be that function for the cylinder. Okay, that way that as we move throughout this shape here, we allow the radius to change by that thing there. And then 0 to pi for theta, because that's kind of where the shape is. Now, what I said I had questions about was, we can go through and solve that, and that setup is not wrong. However, in solving this problem the way we initially set it up, there's one piece of the algebra where you have to introduce absolute values, and that's why the book's gone through and set it up a different way here. It's going to skip that step. So I don't know that we'll go through all of this, but I'll at least kind of work to that point and show you guys what I mean there. But so the second thing here, this little double star thing, the only difference that's happening here is we have doubled, highlight it, we have doubled our whole integral, and we have cut that theta value in half here. And so if you think about the piece that means we're looking at, we are now just looking at this portion over here of our graph, and then again doubling it since it's symmetric. So that's what that changes on.
So what it's saying is the other half of that is going to be negative values in circles.
Sort of, only because of the way we evaluate the integral. It's positive values in terms of the volume, but in the way the integral works, there's a part where you have to raise some, it'll come in just a minute here, but just because of the way you solve, you get negative numbers when you shouldn't, and that's why it cancels out here. I will say this now, if I gave you something like this in a test, I'm not going to expect you guys to recognize that. I mean, seriously, 2 math teachers and a whole weekend later took me to find the answer to this. This is not going to be something I'm going to expect you guys to see and set up there. I really care about the setup, and this setup is not wrong. Okay, that first setup is A-okay to go through and do. And if you plug it into your calculator gives you the right answer also. It's just when we go through and do the math ourselves, there's one little point where you just have to be careful with your algebra. Okay? And I'll point that out in a minute here. So this step, we'll go through and do it the way the book did to eliminate that problem. So if we miss it, that's okay. In general, I don't really like this method of splitting it in half and doubling the area, because if your shape's not symmetric or your density is not symmetric, this is going to mess it up here. So we do have everything symmetric in this one, so it's okay. Like I said, for this problem, mathematically it makes it work out better, but I still don't think this is a good method to try by default, just because there's more things we'll have to check most of the time. However, for this one, let's go from there. And like I said, we'll at least get to that problem, that part where the problem. Integral of r with respect to z. So let's copy down all this outer stuff. All right. Integral of r respect z. Well, r is just a constant, so it hangs around, and so we're gonna have r times z from negative square root to positive square root. And still the r.
Nicole,
Yes.
do you think that like set up a problem like this since the certain maybe is at the origin? So can you just set 2 sine theta equal to 0 and then go that route? Because it would hit at pi over 2 and then negative pi over 2. So doubling, wouldn't that work that way?
Yep, that'd be an okay way to do it. Yeah, that's a fine way to approach it also.
Okay, but if you would have had like the negative pi over 2 and then make it go to pi over 2, would that still give you the same answer?
Well, negative pi over 2 isn't going to work because negative pi over 2 takes you down here.
Okay.
Well, I think that'll be okay because cosine, I think that'd be okay to do it that way. Negative pi over 2 to pi over 2 and then not double it. Is that what you're saying?
Yeah.
I think that'd be fine to do it that way too. I'd have to go through the math to double check, but that should be okay.
Okay.
I'll try to remember to check that later and let you know if it's wrong, but that should be fine.
Because you talk about all these.
All right.
Yeah. All right, so from this 0 pi over 2, 0 2 sine theta. It's going to give us r times the square root minus the negative. So we're going to have, and I'm trying to skip some steps here so we don't go through, take this long there. 2r times the square root of 4 minus r squared. Okay, when you go back and plug in the first square root, then minus the negative, it's going to end up being twice that value. From here, this actually isn't too difficult. We can use u substitution. If you want to pull that 2 out front, that's fine. If you want to leave it there, that's fine. But we can use u substitution for this if we let u equal the radicand. And now we do it with that negative sign, so I'll plot that to the other side there, but that takes care of that 2r also. So we still have 2, antiderivative from 0 to pi over 2. You can go back and find new limits in terms of u, but your limits now are going to be a little more complicated just because you've got that the function you're plugging in here. So I am still going to go back and back substitute. And I know this is not the way everyone does it, but that's my little reminder to back substitute. So this is going to be negative square root of u du.
That 2 is wrong, isn't it?
This 2 is right here. So
Oh, yeah. Okay.
This 2
Yes.
is taken care of by this 2. The other guy's still going to be there. That's fine. All right, so I will pull out my negative also so I don't forget it as I work through. So negative 2 from 0 to pi over 2. U to the 1/2 is going to be u to the 3/2 times 2/3. And again, my negative pulled all the way out front. Going to need to back substitute. I'll do that in just a second. And then this is the step where the little arithmetic or algebra error kind of causes some problems here. Actually, let me call that 2/3 also. That's going to be negative 4/3. All right, so if we back substitute, this is going to be 4 minus r squared 3 over 2.
Is there a negative?
I pulled the negative all the way out front here. Because I forget to type negatives. So if I put it out front, I'm less likely to forget it. All right, so negative 4/3, 0 to pi over 2. And if we go back and do this substitution here, we have 4 minus 2 sine theta squared is going to be 4 sine squared theta to the 3/2. And if I go back and plug in a 0, 4 minus 0 is 0, so 4 to the 3/2. Okay, and I'll stop here because this is where the problem comes in. So from here, if we go through and simplify this a little bit, in that first set of parentheses, we can factor a 4 out, but then we're still left at 1 minus sine squared, which is just cosine. I lied, I'm going to write one more step. Okay. So negative 4/3, 0 to pi over 2. This whole set of parentheses here is going to reduce down to 4 cosine squared theta to 3 over 2. And that's just 8. Okay, so that's where the problem occurs there. So if we take 4 cosine squared to the 3/2, we can reduce that. But when we go through and take that square root, we have to guarantee that we still have a positive value out of there. And that's the part that I skipped doing it myself. If we just let that cosine squared and that 3/2 reduce down to just cosine cubed, that's where the problem comes in. That allows the answer to still be something negative. We can't get a negative value out of this. We have to make sure that we still have a positive value out of this here. So technically, we should stick absolute values around this whole thing. However, since we went back already and are just looking at the positive portion of this for cosine, it's not going to be an issue for us. If we would have gone the whole thing from 0 all the way to pi, that whole quadrant 2 allows cosine to be negative, and that's why this thing had problems there. So if you finish solving it this way, there's nothing you have to worry about. Everything works out, it's just A-okay. But if we wouldn't have made that change in the beginning to look at just the positive portion for cosine, then here we kind of get things to cancel out there.
Is that just the reverse of like double angle? How does it go with sine and cosine?
So from here, this is like 4 times 1 minus sine squared.
Which is, okay.
It uses diagram handy. Okay, so I'm not going to finish it. It's not a whole lot more work from here on out. You do have to go through and use some methods from Calc 2 to deal with that cosine and cube, but it's not that hard to go through and do there. So just ... There's more work here. Eventually, we get 16 over 9 times 3 pi minus 4. And I'll note this is some Calc 2 stuff. Again, it's not really difficult. Some of the easier stuff in Calc 2, but it is some Calc 2 stuff that shows up there. So, multiple things about this problem that kind of run into issues there. The good thing is, if we can get it set up either the initial way we did from 0 to pi or the other way, technology handles it well. Okay, so us doing it by hand is a lot more work than just using your calculator. And Stephanie had asked questions too, like on the test, how much am I going to expect you guys to work through these problems? How much to set them up? On harder integrals like this, I want you to be able to recognize that polar coordinates are more useful, and I want to be able to set it up. I don't need to see a whole page worth of work. Selfishly, I don't want to grade a whole page worth of work for every single person, okay? But if you can get them set up, that's going to be the important piece there. If you can recognize these polar coordinates, that's again an important piece there. The ones I'll expect you to go through and solve will be a little simpler. I do want to make sure you can work a triple integral, but I'm not going to give you tricky things like this. It'll just be a lot more standard, more polynomial type stuff that you're going through and solving, because they're much easier to do. Okay. Example 2. Find the mass of the ellipsoid given by that equation that lies above the xy plane. The density at a point is proportional to the distance between the points and the xy plane. Density we know, or I'm sorry, mass we know usually leads into centroid problems here. We're not going to do a whole centroid problem with this, but similar idea to what we have with that. To find the mass, I won't write the whole equation out, but we basically are going to need to take the volume and then multiply it by the density. So we do need an equation for density of this guy. Okay, oops, x, y, and z. Density depends on all of them. So what equation can we write for the density of this?
Proportional distance between the point and x, y.
Yeah, so proportional means we know we're going to multiply by k, right?
So it would be k, x, y.
Even simpler than that. Distance from the xy plane, right? Xy plane is this flat plane here. What?
Oh, kz.
Yeah, times z and k. The job of z is to tell you how far up you go or how far you are from the xy plane. So we just need to multiply that by z. And that is going to be our density function here. Okay, nothing too crazy on this one. If it was, no, I won't bother. Okay, that is the density function here. So to get the whole mass of the system, we're going to need to figure out limits of integration. I'll leave spaces for that for now. Times, or not times, but the integrand is the thing we just came up with, the density function there. Should we do this as a rectangular problem or a polar coordinate problem, cylindrical coordinates? Why?
Circle region.
Yeah, okay, if we think about, oops, graphing that whole shape there, the whole ellipsoid obviously isn't a circle, but if we think about where this thing intersects the xy plane, so when we go back and let z equal 0, or look at a graph of this, what we're going to end up with, 4x squared plus 4y squared equals 16. We divide everything through by 4. Okay, we do indeed have a circle with a radius of 2. So yes, cylindrical coordinates or polar coordinates are going to be a lot easier to use on this one. Okay. Let's choose. Okay, so if we're going to go with polar or cylindrical coordinates here, we got to make sure that we include that times r in our integrand. Okay, we'll do a conversion, put that in there. And let's stick with our default dz, dr, d theta. Okay. We don't have to mess with the density function on this one because there is no x and y in it. It's just in terms of z, and z in polar, z in spherical or cylindrical is the same as z in rectangular. We have to go back and change that. But if this for some reason here had r and theta in it, we'd have to go back had x and y in it, wrong letters. We'd have to go back and rewrite it in terms of r and theta instead. But this one we don't have that. Okay, so limits of integration for z. What are your innermost limits?
Is it going to be the equation?
The equations are going to be part of this. We're talking about above the xy plane, right? So the bottom's just going to be 0. And so, yeah, let's go back to that equation again. We are going to need to rewrite that guy.
So it's going to be square root of,
What do square roots involve?
so square root of 4 minus r squared.
Square root of 4 minus,
R squared.
Almost.
Z equals z, right?
Z does equal z, that's true. Let's back up a little here. So if we think about this, those first two terms, you can do the long way or hopefully recognize it's like 4 times r squared.
Okay,
So just you reduced your coefficients too much a little. So z is going to equal a positive or negative square root of 16 minus 4r squared. Okay, we could factor out a 4 for both of those and then have the way you did 2 out front if you did it your way, just 2 times your square root. So either leave it this way or simplify down a little bit. But we'll just cover the top portion of this. So we will have the positive square root of 16 minus 4r squared. What are the limits for r?
0 to 5.
No, well,
Oh, I'm sorry.
0 to 2 and then 0 to 2 pi for this guy. Okay, since we're talking about a circle of radius 2 over here, that's why we're going to have from 0 to 2 for our limits. Then the whole entire circle is what I go 0 to 2 pi.
How come in these corners they won't cancel out?
And there's nothing obvious about it. When you go through and solve this one, there's never going to be any trig problems with this one. This is all just polynomials and square roots. So when you go through and do your evaluating, do your substitution, you never come to a point where you have those issues with forcing something to stay positive and then allowing it to be negative there. So like the problem here on this one is the answer to this has to be something positive, right? Because you're taking something and you're taking squared, which means it has to be positive. Squared has to be positive. So that little thing there has to be a positive value. However, when you reduce this thing down, if you simplify this, we get 2 times cosine of theta to the third. And it's possible that can have negative answers. And so that's why we had a problem, is we had this first phrase that had to be something positive. But then when we reduced it down just because of how square roots work, we're left off with something that could be negative. Technically, what we should have here for this one is something like this, the absolute values of that. And we never run into an issue like this on this other problem. On this problem here, there's really no trig involved. We don't have any limits of integration that are trig. We don't have a function that's trig. There's never any trig involved here, so we never see that problem. This one actually isn't too bad to go through and solve yourself. There's nothing really tricky about this one. It's just a bunch of u substitution and clean things up. But let's just do the answer. So 16k times pi.
I have a question.
Go ahead.
So how do we know it's from 0 to the square root of 16 minus 4r squared? Just because on the homework there's a lot that were from the negative value of that square root to the positive value. How do we know it's 0?
Since this says we're finding the mass of the ellipsoid that lies above the xy plane, that's really right, because we have just that top portion of the ellipsoid. We're just cutting off the bottom.
Gotcha.
Out of that, we can just do the last piece here in pi, right?
Say that again.
We could change it from 0 to 2 pi to 0 to pi.
And then multiply it all by 2.
We have to do that too.
Yep. Because when you go from 0 to pi, you're basically just saying now I'm looking at just the from 0 to pi, just the top portion of this piece here.
Right.
So the whole bottom portion we still have to find the volume of. And as long as it's symmetric, we can just double it.
Can you? Well, you wouldn't want to because we're looking for the half part.
But we'd rather that part taken care of, like Cole was saying. If this was going to the negative square root.
That's what I'm saying. And if I'm just saying, would that be an interchangeable part then?
Sort of. Yes, in this case, because the shape we're working with. If we have an ellipsoid, no matter how we cut it in half, that's half the volume, and the part missing is the other half the volume. So if we cut it in half the long ways or cut it in half the other way, half is still half. So it works out to be okay in this case, but that's not always going to be the case there. If you think about like a paraboloid, that kind of just goes like this and doesn't taper off and again. The top part of this is totally different from the left-hand side or the right-hand side. So yeah, so for this one, yes, that would work, but don't default to that.
No, it would suck more to do it.
Oh yeah, it would. It would definitely be harder. Yeah, since your shape is symmetric, there's a lot of different ways you can cut this thing up. If you wanted, you can look at just one octant and multiply it by 4 to fit the top. There's a lot of different ways you can set it up here. So. Good question. All right. So I know I skipped all the work there. Really, this one's not too hard. This is one that I could expect you to kind of do yourself, but we'll see if we can get this section finished. Okay. Spherical coordinates. So cylindrical coordinates are basically just polar coordinates in 3 dimensions. We still have r, we still have theta, we have z. If you recall what spherical coordinates, and that looks like a whole lot of stuff there, but spherical coordinates' job was to say we are talking more about like latitude and longitude. And I will just bring up a picture instead of find the whole thing. That website, because that website's awesome. So if you recall what spherical coordinates did, is they gave you this information here. So r, or rho, was talking about the distance that we were from the origin. So it's just the radius of a sphere that we're working on. Theta is the same theta that we had back in polar coordinates. It's measuring your angle from the positive x-axis. So as theta gets larger, we're going all the way around this thing here. And the other new piece we had to work with was phi. And what phi does is measuring your angle from the positive z-axis. So when phi is 0, you're on the z-axis. And as it gets larger and larger and larger, we're going further from the z-axis there. We did have the restriction that phi was only between 0 and pi, because otherwise we'd kind of loop back and it wouldn't really work. But r and theta, or rho and theta, hopefully are a little more familiar with. These coordinates work out well when we have a spherical shape, so like a sphere. If you're working with a sphere, or cones are also really easy to represent in spherical coordinates too. If you're working with something like that, these coordinates work out a little better. We haven't worked with them as much, so they're a little clunkier to kind of deal with, just because we don't have as much practice with them. But in some cases, they are going to make the math easier. And then even in terms of technology, if you program the technology to do it the most efficient way, everything's just going to run faster and run smoother. So another kind of reason to pick up on this. This is all stuff that we've had before. This is just review from things we've seen in the past. This is the way we go back and do our conversions. So the first two are going to take you between spherical and rectangular, and the last one is meant to go more from, well, I guess just different ways from spherical to rectangular too. They're all kind of the same thing there. All right, the integral for this, we're not going to go through and reason the whole thing, but we're starting off with some triple integral over here. We're going to have to go through and decide z and y and x and order and all that stuff there. When we go through and do this in spherical coordinates, we're still going to decide the order of integration, but we'll call d rho, d theta, sorry, d phi, d theta our kind of default. We're going to have to make sure we go back and convert all the limits. We're going to have to go back and convert the whole entire problem. And then the piece we're going to multiply by here is going to be rho squared times sine of phi. So like when we convert to polar, we're going to multiply by r. When we convert to spherical, we have to multiply by this. Like we have to have that piece there to make these conversions work out. Okay. So example 3, find the volume of a solid region bounded below by the cone and above by the sphere. So we've got a cone on the bottom portion of this, sphere on the top, kind of like a little ice cream cone. That's what we're looking at here. The reason this works out nicely to use spherical coordinates is both these shapes simplify down really nicely in spherical coordinates too. So let's take a look at that first. So in spherical coordinates, the easy thing about the sphere is if we look back to the formulas up above, x squared plus y squared equals rho squared. And so we know rho in this problem is just 3. We have a sphere with a radius of 3. And this is why spherical coordinates work out nicely. Rho equals 3 is a much easier equation to work with than x squared plus y squared plus z squared equals 9. Okay. Now going from that cone to spherical coordinates isn't quite as easy there, but we're going to need to do it in just a minute, so we'll get to that then. Okay. And I don't want to actually write that equation there. We're going to do something a little different there. So anyway, spherical coordinates are going to work out really nicely for this. Let's go through and start setting up our volume. We'll get to the other equation in a minute. We don't really actually care about that equation itself. We're going to modify it a bit. All right, volume means the integrand has to be 1, so we don't have to add anything additional here. But since we're converting to spherical coordinates, we do have to have that rho squared sine of phi. And then let's stick with that default d rho, d phi, d theta, and see if that's good enough. The challenging part of this is, again, recognizing and choose this coordinate system. We haven't worked with these as much, so it's not as obvious. But then coming up with limits of integration requires a little more thought, again, because we haven't worked with this one quite as much here. So think about inner limits of integration. And I don't have this guy graphed. Maybe it would be a little easier if I graph it.
Yikes.
I actually just like these to graph things.
Yeah. It's only 3 days.
Okay, there's our sphere. Maybe I'll graph the cone too.
I'm just
Did not type that right. There we go. Okay, and there's our cone. And again, I don't know how to make this zoom in on just the part we want there. But imagine looking at the inside of this sphere. You can see that kind of cone shape on the bottom and that rounded top. That's what we're going to go back and find the volume of. Okay, that piece kind of inside of that. All right. So we need our limits for z. Okay, z is the same here, or sorry, rho, wrong thing. And our limits for rho. What is the smallest the radius gets for this shape? What's the lower limit for rho?
0.
0. And then what is going to be our upper limit for rho?
Circle.
It is going to be the circle. Okay. Now everywhere on this shape it has the same radius. If you go from that inside and goes to the outside of it, no matter where you're at, it always has the same radius. There's no like bubbles or dips or anything like that there. And so on that sphere it has a radius of 3, and so that's going to be our upper limit. Okay. Very easy inner limits to work with. Okay? I mean, those are not challenging at all. They're just constants. And so again, that's why this is a lot nicer than trying to work with square roots of a whole bunch of stuff there. Okay, so out to phi. Now remember what phi does. Phi's job is telling you the distance, the angle mark from the z-axis. So we're always going to start here on that z-axis since our shape is touching it. We don't have like a gap around the z-axis. And then what we need to know is how far down do we go? And what part of this function or what part of this equation decides that? Is that really the sphere's job or is that the cone's job? Yeah, that's the cone's job. So what we need now is say, okay, well, this cone, where does that thing stop? It's always going to stop at the same point all the way around the shape here. We just need to know what angle it is from that blue z-axis down to the side of that cone there. So the way we can go through and find that, so I'll note, need to see where the cone is. Specifically, we want to know where the cone, or we can go back and look at where the cone and our sphere intersect. That'd be a good way to kind of hone in on what we're going for. So let's see where the cone and sphere intersect. Another way to kind of think about this is, remember, after we get those inner limits, we've often gone and done and said, well, what's this region of integration? And that's really the same thing that's happening here. If we think about that region of integration, the way we have been before, we're trying to say, okay, well, looking down on this, and I know this is a whole bunch of red. I can change the color, maybe. Yeah, we'll just leave it. Currently. All right. Okay, so we're looking for where that circle and that cone intersect. So this kind of red part in the middle is what we're trying to find there, which it is a circle. So we need to kind of know the equation for that. But again, in spherical coordinates, we don't really care about the circle so much. That's not simple to work with here. Anyway, where these two things intersect. So we've got x squared plus y squared plus z squared equals 9. We've got z squared equals x squared plus y squared. And we're not really solving this system because we've got two equations with 3 variables. We're trying to just rewrite this guy here. And we've done a similar process to this before. Since x squared plus y squared equals z squared, we can go back and replace that first equation, the x squared plus y squared, with the z squared. So let's do it that way. So putting that second equation to the first, we're going to get z squared plus z squared equals 9, or 2z squared equals 9. And so if we take the square root, we're going to get z equals a positive or negative square root of 9 over 2. If z was negative, we'd be underneath it, and we can tell from looking at our picture that we are on the top portion of this, so we know we're not caring about the negative square root. We just want that positive. And if I try to reduce this a little bit, we can write that as 3 over square root of 2. Okay, or if you want to rationalize 3 root 2 over 2 is okay also. So really all this is saying right now is where this cone and this sphere intersect, this region I care about, is right there on that plane z equals 3 over square root of 2, which still doesn't tell me what phi is equal to, which is really what I want to know here. But if we go back to this piece over here, okay, we know that z equals this, and that's going to go back and tell you what phi is, so we're going to go back and use that. So we know what z has to be. We already know that rho has to be 3 at this point, that's where those things are intersecting. So with a little bit of substitution, we can go back and find phi. All right, so z is going to be 3 over square root of 2. Where these guys intersect, we know that rho is 3. And cosine of phi is what we're looking for. So we can divide both sides by 3. Maybe you recognize that as a familiar thing, but if not, think about rationalizing. That's the same thing as root 2 over 2 equals cosine of phi. And now what does that mean phi has to equal? There we go. Okay. So it turns out that, yeah, a cone is a lot simpler to work with in spherical coordinates, but getting to that point is definitely not like short in one step. I mean, those aren't really obvious things to go back and do there. And really, the only difficulty with this is we have to work with this coordinate system a lot. If we were to work with this coordinate system more, this would seem a lot easier. But it's not something we deal with a lot here, so it seems a little weird. But phi equals pi over 4. I mean, if you think about it, it kind of makes sense. If you go from that z-axis down to an angle of pi over 4, no matter what radius or what angle you're at, you're creating this cone here forever. Now we are stopping it because they intersect, but that's going to be our upper limit of integration for this, because that's where that cone ends. And then the last one, theta. What does theta range from? There we go. Something we're familiar with. So limits of integration are all very simple here. I mean, nothing's complicated there at all. Even the integrand itself isn't going to be too complicated to go through and work with. So once we've got this set up, it's really a fairly easy problem to do. But getting this one set up is not obvious. Okay, I mean, that's a lot of different ways of thinking about things here. To make sure we have time to finish the last one again. It's not too bad to go through this one. You do get kind of a funky answer, but it's not hard to get to. So we can write this 18 pi minus 9 pi times square root of 2. And it looks weird just because you're taking the sine of root or pi over 4. That gets kind of messy. But again, setup on that one is definitely the most difficult part. We won't use spherical coordinates much. I want you guys to just be aware they exist, to maybe have a general understanding of how to apply them. But I think cylindrical coordinates are a lot more useful. Okay. I'll tell you now, on the test, I'll ask you to set up one problem with spherical coordinates. I'm not going to ask you to work through it. And depending on, actually, I haven't written the test yet, but maybe I'll just ask you to explain why it might be better. But you're not going to have to do this more than once on the test. So don't worry a whole lot about that.
So why might it be better?
Because these equations are a lot easier in spherical coordinates. If you have that sphere x squared plus y squared, the first thing, these guys are the same equation. This is a much, much simpler equation to work with.
Yeah, okay.
And then same thing with our cone too. For that whole cone, theta equals pi over 4, or z equals pi over 4, is a much easier equation to work with. And that's really the only benefit it has, when you're working with some equations, some shapes are a lot easier in spherical coordinates. Pretty much cylinders, nope, try it again, cones and spheres. Cones and spheres are the two that simplify down a lot in this coordinate system. Most other ones don't. Ellipses don't. Paraboloids don't. But spheres and cones are nice here. All right, so let's use this stuff here, the whole setup and thing, to do one more, just kind of more applied problem here. Last one in this section. Find the center of mass of a solid of uniform density for the described above shape. Okay, so we'll use that same little cone shaped piece here. We just want to find the center of mass of this. And if you recall, to find the center of mass, we're going to go back and say, okay, we need Lorentz integration. We need some density function. And I wrote as x, y, z there. We'll have to fix that. And then go back and just plug all parts here. But like we said on the last one, we could go through and try setting this up, and that would be okay to set this up with rectangular coordinates. But it's kind of a mess. And the main reason it's a difficult thing to do there is just due to the kind of the shape of all these pieces here. You're gonna have a lot of square roots that you're going back and substituting in. The integral itself is gonna be very difficult to work through, but you could theoretically do it in rectangular coordinates. But we use the same ones we had before. So taking the same limits of integration that we did, because those limits of integration are basically building our shape, and we are working with the same shape, so we don't have to do anything different. Okay. If we have a solid of uniform density, what's rho gonna be?
Rho sine theta.
Sine phi, yeah, that's part there, okay? But since this is just uniform density, still put some constant in there for it, because you don't know if it's like uniform density of 1 or 10 or something like that. So still put a constant in there for it, but just something. But then yes, like Russell's saying, when we go through and do that conversion, we have to make sure we include that conversion factor. So rho squared sine of phi. Right, yeah. D rho d phi theta. Now it tells us the total mass of the system. But if you compare this to the integral set up on the last page, what's the difference?
Okay.
Okay, that's the only thing that's different there. K is just constant, right? So just like factor it out front the whole time. We're gonna get the same exact answer for this integral as we did for the last one, just times K.
So all that we did to find center of mass is just multiply by K.
No, this right now is just finding the total mass of the system. We haven't actually found the center of mass yet. Center of mass means you need X bar and Y bar and Z bar, but they all need this. Okay. There's some things we can do to save us a little bit of time here. If we think about this shape is symmetric right along the Z-axis, right?
Yes.
And it's of uniform density, so it's not like a heavy spot somewhere and a lighter spot somewhere. It's the same density everywhere, which means the center of this shape is going to have to be on the Z-axis.
Yes.
So you're more than welcome to go through and find X bar and Y bar, but you're just going to get zeros out of both of them. Okay, and if you recognize that with symmetry, that's an A-OK thing to go through and use here on these problems, especially because there's a lot of pieces to going through and solving them. But eventually, when you find the moment about the Y-Z axis, which you're going to need for X bar, that's just going to equal 0. And similarly, when you go through and find Y bar, which is about the X-Z axis, it's also going to be 0. But the other guy's not, so we'll go back and find that one. And the process we use to find this will be the same thing you use for the other ones, just with different variables in place. I'll mention it in a minute. Okay. So this one we need no matter what. We'll go back and find this. Total mass of the system, we've already got there. And it's a very similar formula we set up before. If you think back to the notes that we had for this, we're going to have that same region of integration. So 0 to 2 pi, 0 to pi over 4, 0 to 3. Oops. The integrand for this is not just going to be the density though. Okay. If you flip back in the notes, you'll see that when you're finding Z bar, you need to have Z times the density here. And so I'm going to write this as Z, but I'm going to erase it in just a second. So leave some room in your notes if you just write a Z there also. But it's Z times density. And we know the density is just K for this problem. And then we are converting it. Okay, but we don't want to leave Z there. Like I said, that's what the formula says. We don't want to leave Z there. What is Z in terms of spherical coordinates? That would be in cylindrical coordinates.
Oh, it's constant. Rho cosine.
Yeah. So when we're converting between rectangular coordinates to spherical coordinates, one of the things we're given is Z equals rho cosine phi. That's what we're actually going to plug in place here. Okay, so we don't want to leave Z. Nothing in this problem should have a Z in it. So instead, it's going to have rho cosine phi. And then the rest of the stuff is explained there. Okay. Similar thing would happen when we go back and find X bar and Y bar. When we take X times whatever, we have to go back and let X equal rho sine phi cosine theta. And same thing for Y. And again, you're more than welcome to work through those. You do just get a bunch of zeros out. But for this one, we get something other than 0. So that would be the problem we go through and set up. A little more difficult to go through and solve it just because we have some trig functions here, but I don't have that worked out. Eventually what we get for this is going to be 81 times K times pi all over 8. Which means really what we care about for this problem is a centroid. X bar is just 0 because you have 0 times the mass. Y bar is just 0, because again, 0 divided by the mass. But then what we get for Z bar is that constant divided by the total mass of the system, which we found on the previous problem, just times K. And so we need to go through and simplify that. K's cancel. Some other stuff might cancel too. Yeah, we could factor like a 9 out of everything. Eventually what we'll get if we keep simplifying this is eventually 9 over 8 times 2 minus root 2. Yeah, because of pi and everything too. So pi's will cancel also. A lot of stuff cancels there. We're about 1.92. So the centroid for this is 0, 0, 1.92. And that's like Russell said, number 16 on the homework. It's a lot of work for one little thing in the end there. A whole lot of parts to set up in this problem.
So why is it, how did you know it's 0?
Simply just because it's symmetric. This little ice cream cone shape we're making is all centered around that z-axis there. And so if we have a uniform density, there's no one side that's going to kind of pull it one way or the other. So it's just still going to stay there centered on z. And really, just because there's so much work in going through and solving these, any shortcuts we can take on these like that are going to be fine. All right. That's 14.7. The last section that we have in this chapter, I'm not going to get to the math for today, but a little intro for it. So everything in this chapter is about working with double or triple integrals. So we have three-dimensional surfaces, three-dimensional solids, and we're trying to find volume, try to find different features of this. And depending on the structure of the shape itself or the structure of the region we're trying to integrate it over, that was able to tell us, well, should we use polar coordinates or cylindrical coordinates or spherical coordinates? What we're going to see in the very last section is kind of a more general case. Is if we've got something that is very difficult to work with in the things we already have established, so either rectangular, cylindrical, or polar or spherical, there's one more way we can go back and kind of convert these to make them hopefully a little bit simpler to go through and solve there. So we'll see this more tomorrow, but that's kind of the idea behind this. When we have these shapes that are difficult to work with and the things we know, it's like one more way we can maybe try to simplify the math. That's not really saying it very fairly, because it's not going to simplify the math. A different way we can write the integrals to go through and solve it. Okay, but if you have questions, let me know. Like I said, no class tomorrow, so Wednesday we'll meet again and we'll be able to get through 14.8. If you do have issues, let me know. And also, like I said too, if we plan on taking a test either this Friday or next Monday, if that doesn't work, let me know. And I'll just kind of work with people on different cases. I think Friday and Sunday for you guys is okay too, but Friday through Monday. Okay. All right. Have a good day.
Monday.